flying home in your small Cessna plane with one passenger in really lousy winter football weather when horrors, your wings start to take on ice. That means that they can't push down on the air as well, so not at the right angle to get the right force, and that means your plane starts to drop. Mayday, you signal the nearest airport, which is still in Wisconsin, but not your home airport, that you are coming out of the clouds. Unfortunately, the problem with clouds is you miss. And you can clearly see the ground under you now, and you can clearly feel from the plane's velocity that you are going to massively overshoot that airport. Mayday, mayday, you are going down. Your only hope is you can actually hit the tops of the trees and not simply crash straight into the rocks on the ground. Ladies and gentlemen, physics saves the day. Part 2, what do you do?
Turn?
Your plane is broken, dude. You're going to crash. If you could turn, you'd have done it half an hour ago. All right, is the goal of this lesson to explain why this Packers fan survived the plane crash that everyone told him he was incredibly lucky to walk away from. Ladies and gentlemen, the Impulse-Momentum Theorem. I will need 4 incredibly responsible, focused volunteers who can listen to instruction and not literally walk out on the job if I stop talking or stop looking at them for all of 6 seconds at a time. 4 very responsible volunteers. Responsible volunteer, fantastic. Lila and Matt and Ari and Evan, fantastic. Everybody take a corner of your red sheet. I'm going to position you maybe here-ish, tall people in the back.
What if I'm not a tall person?
Then you are in the front. All right, you're beautiful. Now hold it, no, you're not in front of the smartboard, please. Hold this sheet way up so that the class can now see the whiteboard. You two down in front. Fantastic, beautiful. Got reasonable clearance from the markers. All right, after 2 minutes of instructions and exhortations, I think it's actually fine, hurry. Someone who is a better pitcher than me will pitch this raw egg at the whiteboard with all their might.
I'll do it.
Fantastic. I was hoping that somebody was better pitcher than me will do this. Now, if we're going to do this first one as a Gedanks experiment, which is German for I hate cleaning up messes. If Matt and Ari demonstrate fall down on the job, what will happen to the raw egg? It will splatter all over the whiteboard. It will be cleaned up in aisle 5. Now, absolutely.
What if I miss?
Well,
I won't miss.
the key for this unit is don't miss. That's why we don't have me pitching. What physics variable would be responsible for the egg's destruction? Which physics variable would be responsible for the egg's destruction? I don't think it's time. I don't think it's color. What physically breaks the egg?
The force.
The force. Yeah. If the egg's going to feel too much force, it's going to crack its shell. All right. Back corner holders sheet.
But then once it falls.
Now, Lila has just demonstrated the potential problem with this demo. People holding the corners, you have to be responsible, and you have to keep hold of the corners no matter what. Look, Elvis!
Got it. I learned my lesson the first time.
No matter what, you've got to keep hold of your corner, and you've got to keep that sheet up. If they all held this sheet so taut that it was basically a wall, what would happen when the egg hit it? It would bounce. It would go flying. It would get egg all over the floor, and it would be cleaned up in aisle 6. So Matt and Ari, your job is to make sure that when our mighty basketball-playing Elisa pitches that egg with all of her considerable strength, you guys do not have a sudden attack of chicken, which has been known to happen to volunteers in years past. Drop the corner of the sheet and power with your hands over your head, which always saves everybody's hairdo and is not so good to the board. Okay. Now, even if you have it at only a moderate tension like we have now, which is great for the demo, the egg is going to bounce. That is why we have our front bounce guards, Lila and Evan. Lila, if the egg rolls toward you, what are you going to do? You're going to gently lift the corner. Evan, if the egg rolls towards you, what are you going to do? Gently lift the corner. Beautiful. Okay. We pause for our annual tribute to the best bounce guard in CJRZ history. This was back in 2006 when we were in the old building, which had industrial carpet all over the floor. The demo happened, the egg was pitched, physics happened, whereupon the front left bounce guard decided that his job for the day was done, dropped the sheet with the raw egg still on it, and began to walk back to his seat. The first I heard of this was the front right bounce guard, Mr. Aaron Magid, who served his tour of duty in the Israeli army, is a teacher in his own right. Oh, I have grad students. And studying Middle Eastern political what's name at Harvard, dropped his corner with a no, and emerged from under the sheet about 1 second later with the raw egg grasped between two fingers, an inch from the carpet. It was beautiful. It was inspiring. Carpet.
Oh no.
You see the nobility and the challenge of the great bounce guard. All right, we go through this every year. I've award every class. For some reason, I think that honors seniors who are 3 years ahead of grade level in calculus and have finished AP Chem know this. But ladies and gentlemen, for the next week's worth of lab, if you put a raw egg on a table, what will happen next? It will fall off the table, and if you're doing this in the lab, you will lose your 5 points worth of egg before your experiment even gets off the ground. Moral of the story, do not put the raw egg on the table. Now, the instant that this raw egg leaves my hands, oh my basketball player, I am forever absolved of all responsibility for the cleanup. I'm putting this plastic cup over here. I'm getting out of the way. All right, you got back corners, you guys have good courage, because I feel nuts. Front bounce guards on the ready. Okay.
I just throw it as hard as I can.
As hard as you can. Can we scoot just a few inches away from the smart board? All right.
We hold it higher. What is
Okay, keep your eyes on the egg. 3, 2, 1, pitch it! Hey! All right, that's in my possession. You guys are off duty. Well done.
Good job, Lisa.
Good job.
All right. Now, let's dissect that force and see what happened. I would like to say what's different between that bed sheet and the board. I'd say there's a fairly obvious answer. Shout it out.
Board is
Board is hard, then the sheet is soft. However, my very first year at the CJ, teaching the Pioneer class back in 2003, I was looking for something soft to throw the egg at. So off I went to the dining hall, borrowed a blue plastic tablecloth that they weren't using anymore, took it back to the lab, stood in front of my first physics third period class, just like you guys, and called for a pitcher. That was Mr. Jacob Cantor. We didn't have a baseball team yet, so he pitched for Skokie, and he was really good. He said, Mrs. Eliezer, are you sure you want me to pitch this thing as hard as I can? I said, as hard as you can. And everybody's banging the lab benches. Do it, do it, do it. And he does the full windup and pitches as hard as he can and pitches that egg straight through the blue plastic tablecloth, leaving an egg-shaped fuzzy silhouette passage in the tablecloth, smashing it to bits all over the whiteboard with radiating egg-shaped stress fractures that you can still see in the whiteboard that is now in the biolab across the hall on Etzem Hayom Hazeh. Go around to the back of the board.
Basically the
Miss
same.
Wolf does not show the class, and you will still see the little egg-shaped crowns. And my honors class thought I had set him up and just about fell off their lab stools laughing while poor Jacob Cantor looks at the mess on the board and wonders if his physics teacher really means for him to clean that up. No, I did not set him up. However, I demonstrate unto you that apparently soft is not the answer, because we tried different kinds of soft. Apparently some of them work and some of them don't. We need an actual physics variable to quantify what difference the bed sheet can provide, and this bed sheet lives in the physics lab from then on, in case anybody needs anything soft and doesn't have to worry about tensile strength in order to figure out what's going on. 1, 2, and then equations.
Well, when you throw the egg at the sheet is able to move with the egg compared to the wall, which is regardless of what the egg does, it's just going to stay there.
All right, and we're going to quantify that movement with one variable in this unit and with a slightly different variable in the next unit. All right, ladies and gentlemen, the Impulse-Momentum Theorem. The force is the problem. According to the test that almost half of you have taken, if we have one force, how does that relate to motion? Newton's second law, hit us up. All in time. One small substitution, we have the Impulse-Momentum Theorem. Here it is. Force is mass times change in velocity over change in time. If we want to write it as the fraction way, the impact force, or the interaction force we'll feel, is directly proportional to the mass, directly proportional to the change in velocity over the impact, and inversely proportional to the time. These are Newton's third law forces. That means we have to label them all. This is an impact force. This is an impact time. This is a change in velocity over the impact. How many velocities do you need to know to find a change in velocity? Two. Which two?
Before or
That's
initial
it.
and final.
Initial and final, before and after. Hey, that sounds like we're going to be doing before and after in this chapter, and son of a gun we are. Let's check. Given that Matt and Ari did their duty and did it well and kept that sheet up, did that change the mass of the egg?
No.
What was the initial velocity of the egg? During the impact, it was very fast. Who was responsible for that? Alisa, did you pull your punches? Did you do a wimpy throw simply because you knew the sheet was in the way? Or did you throw as hard as you could?
Not as hard as I could because I was scared I was gonna miss.
Fair enough. But did you throw
hard,
fast?
No. Yes.
And if Matt and Ari had dropped the sheet and run screaming, would that have changed the initial fast velocity at which you pitched?
No.
No.
Absolutely not. What was, trick question, the final velocity of the impact? 0. None of these variables have changed. Therefore, what did the bed sheet provide that the wall did not provide as well?
Oh, it's a bigger time.
It's a bigger impact time. Let's do this slightly in slow-mo, and let's explore what Matt said about motion. Can I have 4 big, strong volunteers? This is easier. There's not going to be any raw end. 1, 2, 3, 4. Come on up. Everybody hold the corner of the bed sheet all vertical this time.
I'm coming.
I think it was you, Joseph. You go, Joseph. You got it.
Okay. All vertically. All right. You want to keep some of that down near the floor. Hold that up. I want to make sure I miss Josh and Mayan's desk all the way up. You guys down all the way up. Vertical sheet, not horizontal. Okay, scooch a little bit this way. All right. I'm going to run at top speed. I'm going to crash into the sheet. Everybody holding tight?
Okay.
Consider the difference in time between when I actually hit the sheet on this side and when I stop. Okay, did you guys see the impact time?
Yeah.
Did you guys feel the impact time? Would on the order of, seconds-ish, what would you estimate? How long did it take you guys to actually bring me to a stop?
Less than
Okay.
2. Less than 2.
All right, so we're talking, it sounds like 1 second plus or minus 3/4 of a second, including your half a second and the other's almost 2 seconds. All right, that was the impact time. Did my glasses sustain any significant damage as I simply charged into something head on? No, because I had a huge impact time thanks to my 4 stellar volunteers holding the bed sheet. If I try that again with the whiteboard, I will not have any glasses net, and the jury will still be out on what happens to my nose because that is an incredibly short impact time. I'd say it's immeasurably short, only we're starting the lab next class period and going next week to actually measure the impact time of something dropped off the lab bench and smashing itself to bits, or not, on the ground below. The shorter your impact time, the bigger your impact force. The larger your impact time, the smaller your force, and the safer you'll be. If you want to move the delta t to the other side and kill the fraction, you will notice that if you apply a force over a certain time, it will take a mass and change that mass's velocity. This is impulse. This is not momentum by itself. Notice that change. This is a change in momentum. We said an object will in motion in the same velocity unless an outside force interferes. This is how the outside force interferes. It interferes over a period of time. We call that delivering In my case, it slowed me down. Elitza on the egg delivered an impulse to speed it up. Lots and lots and lots of examples. I'm going to put these on the board so we can take board photos for absentees. Example number 1 is the Cheesehead. The Wisconsin Packers fan who had maybe 15 seconds before his plane crashed full on into, and yes, he did hit the trees, grabbed the giant Cheesehead that he had brought with him to Cleveland to show himself a true Packers fan and put it on and cowered under it. I ask you, it's almost 12 inches of solid foam. How much impact time do you think it took to stop the ground and the front of the plane going through an enormous foam Cheesehead?
More than if he
Yes.
wasn't wearing it?
Absolutely, hundreds of times more. That meant he felt hundreds of times less force. Now, his legs couldn't fit under the Cheesehead. He did break his ankle, but he was interviewed by reporters from his hospital bed saying that he was able to hop out of that plane just fine and assess the damage. That Cheesehead saved his life.
Were other people harmed?
No, the other guy also sustained minor injuries but was fine.
It was like it was a
2 people flying back from Cleveland in a Cessna to a rural airport. Yes, Cheesehead saved the day. It provided him with hundreds of times more impact time than the regular collision.
Does it matter if the direction of the impact is horizontal or vertical, or is it the same regardless?
And it tremendously makes a difference because it's a question of what's the shape that's protecting you in each direction. All right, next piece of anecdotal evidence. Example, notes. Welcome to the 1950s. World War II is over. The war solved the problem of the Great Depression. The massive increase in industrial productivity to support the war effort. Now the war is over. All boys are home. Running things on the home front is told, congratulations, women, we knew you could do it. You're fired now. Your job is to find a man and keep him happy. We've got good old-fashioned American steel made in American factories, born in the USA. It's kept in this country and not being sent overseas to the war effort. And we have cars made of solid American steel through and through. And now that we're coming home and raising families full of boomers, now that the war is over and we have something to live for, truth, justice, the American way, as long as you're white, male, straight, and live on Long Island, we want to keep these possessions. These are valuable possessions. We don't have to ship them to Europe. These cars are as solid as they come. I ask you, if you take a car whose frame is made of good, solid American steel, and it crashes, tell me about the impact force that that driver will feel.
Well, if he's an airbag, then.
Aha, this is the 1950s.
No bumper.
Doesn't the
I don't feel the
Not
same
yet, it
effect
doesn't,
as
not in the 1950s.
It'll
Tell me
hurt.
about the impact force that this driver is gonna feel.
a lot of impact?
It's
A
gonna
lot.
be ridiculously huge. This car will be fine once you straighten out the dent in the bumper and deliver it to the unfortunate heirs of this ex-driver. Yeah. An object in motion tends to stay in motion until an outside force interferes. What was in front of this driver when he hit the wall? The steering column. It was not unknown of for people to be found impaled on their own steering columns. It was dreadful.
Steering column? Oh,
Yes.
yeah, right. Like behind the wheel?
Yeah. Now, also about this time, late 1940s, one of the veterans returns from World War II to get a job in an auto factory in Detroit. It's a good job. He's happy with it. And one morning, everybody's ready at 9 a.m. They turn on the production line, but it turns out there's a small hole in one of the rubber hoses delivering compressed air to the machines. Well, that's a problem. Fortunately, everybody knows where the problem is because it so happened that there was a heavy, greasy burlap tarp that was draped over the hose, and that's why they didn't see the hole before they turned the production line on. They turned the production line on, the tarp goes
whoosh, all the way to the top of the ceiling. Well, either the factory's possessed or we have a compressed air leak right under where that tarp is defying gravity. So, of course, the foreman shuts down the production line, the hole is very quickly patched, and we're up and running only a short while later, and everybody forgets this episode except this one veteran who's working in the factory, and he says, "Oh my God, I have never seen anything move that fast in my entire life. I survived the Battle of the Bulge, and I've never seen anything that moved that fast." If only we had had safety systems that could deploy this fast, some of my buddies would still be walking around on 2 legs and not be holed up in the VA hospital. He said, what a safety system we could design with compressed air and burlap cloth. What did he invent?
The airbag.
He invented the airbag and got a patent for it. And it's just unforgivable hubris and ridiculousness on the part of this country that this technology didn't immediately become standard for every car in the 1950s. It wasn't until the 70s and 80s that they started saying, hey, check out what this guy invented in the late 40s. Wouldn't this save hundreds of lives in road accidents? And now we have 2 things. What does the airbag do as we update the diagram? What's its purpose as far as physics is concerned?
Increases
It increases impact time. Now, nobody has found impaled on their own steering columns because in order to get anywhere near, you have to fight your way through a bag of cloth that is really fighting very hard to push you back with all the strength that compressed air can deliver. If anything, may Tom mention her family's business has dealt with lawsuits talking with over-enthusiastically deployed airbags where the airbag fights you, it wins, and the only people I know who have sustained minor injuries in car accidents, it wasn't from the impact, it was from impacting the airbag. They were back at school in 3rd period by 10:30 a.m. So that's what I mean when I say minor injuries. Second, several people mentioned the body of the car, which is no longer the solid steel frame. Most of the frame here is made of aluminum. What does aluminum do when it hits the wall at 30 miles per hour?
Crumple.
It crumples, and that's the invention of the crumple zone. Again, physics. What does the crumple zone do?
Increases
It increases the impact time because your car will not stop moving until the entire front hood has been reduced to a useless ball of crumpled metal. Now, if you try that with an internal combustion engine, you're probably going to blow at least half the block sky high. Do not crumple an internal combustion engine full of gasoline while it's running. So what happens is that your car has rails, not wholly unlike the rails in your oven with a little notch on it. Like if you pull on them, they won't come out and spill your kugel all over your feet. But if you really know what you're doing and you pull at the correct angle, you can kind of tip them down and up again, get past that notch, and then draw the oven door out. That rack is not going to do anything unless it's hit with a front impact at top speed. But if it is, the engine will be pushed over that little notch, down, out, and under the passenger compartment. You will end the crash with the engine under your feet, uncrumpled and whole and not catching anything on fire, while the aluminum hood in front of you is crumpled in front of into a useless mass. We call this car totaled. The engine is under the passenger seat. It's practically on the ground. It will never drive again. You will be a very mad driver when you get out, take out your cell phone, call for a tow, and start shopping for new cars online while you wait to be picked up. You will walk away from this crash with a few minor bumps and bruises and get a new car, as opposed to here where the car would be drivable away from this crash, but you need to get a new driver. We've got 2 huge rounds of increased impact time here. One for the car and one for the passenger. Increasing impact time every time. True story. Why did it take us more than 10 years to get a wrestling team? It wasn't through lack of interest. It wasn't because wrestling is not a Jewish sport. Because there was a brilliant article written by an Israeli yeshiva student about how wrestling for Ida Crown made him a better Talmud scholar, and he proved it too. He said, your opponent does not care about your NCSY convention last weekend. You do not practice, he will flatten you. Stop whining, get your butt out of bed, and go do practice. This does not work on my math teacher. It does not work on my Hebrew teacher, but my wrestling coach does not have to argue with me. I came from America. I went to Israel. The other buffers don't care that Hebrew is not your first language. You do not prepare for Seder. They will flatten you. Stop whining, prepare for Seder. It was beautiful. That, what
Because we
problem?
needed mats, and the
Oh,
mats
come
are extremely.
on! Community centers have leftover
That's
gym mats
true.
all the time. Kindergartens use mats to nap on. I'm sure we can find something used in blue and nice and soft. Why won't that work?
Because the wrestling mats, I don't know exactly, but
They're
they're like
Yes.
have a
What
specific material that's padded so that
For
like
what?
if,
What are you paying for?
Increase-
when you
increase
when you
impact
throw a
time.
dude
Yes.
onto the mat.
It can't
Don't
just
steal
be
my-
soft.
I didn't
Or
steal
it needs
it.
a special
No, I
polymer
disagree.
that is
I get
associated with a
it.
certain impact time. What impact time? Well, remember, wrestlers are in different divisions by mass. They are actually sorted by mass.
Whoa.
That's why you
Yes.
can't like.
Now, velocity,
Are you in the
square root of
100
2GH, conservation of
Wow.
energy, take the height of your average wrestler. Oh, that's right, they're also sorted by size. Take center mass, rotate, throw from that height, what's the velocity going to be? You need the impact time to be big enough, not too hard, such that you've got a small impact time and the wrestler gets hurt when he or she gets thrown, but not so soft and squishy that, like a nap mat that takes no time at all to go through that. It has to be very, very, very carefully calibrated in
And that's
between.
why
And that's why wrestling mats are so prohibitively expensive. We had wrestlers, we even had volunteer coaches, but it took us 10 years to raise the money
I was
for
a
those
wrestler.
wrestling mats.
When I did gymnastics, it was almost the opposite. You had like the thickest, softest mats possible because you were like often like landing on your head and like in really weird positions. So like you had to have really thick, soft mats to be able to like absorb as much impact as possible, and that's like what the foam pit is.
That's there to increase the impact time. The foam pit is about the depth of this room, and it's full of incredibly high friction cubes of foam that stick to your socks. How long do you think it's gonna take to plow through 10 feet of high friction
I
squishy?
planned
You
for that a
won't.
very long, painful time.
And even if you're flipping over and over from, a high launch speed, a high gravitational potential energy, a high kinetic energy, if you have an impact time on the order of a second, you will be discomfited, but you will not actually be hurt. Questions about increased impact time and how it saves the day?
Well, that's
This is the fraction form of the Impulse-Momentum Theorem. Let's try the non-fraction form. We've got the windup and the weapon. I don't blame Elitza in the slightest for being worried that she was missing and really not giving it her all. We've had 2 people since we came to this building who ate at a giant blue bench sheet and missed. I never would have thought it possible. Teenagers, I love them. They always surprise you. Elitza threw like this. My original pitcher, who took me at my word, threw like this. Which throw took longer? Yes, the windup takes the force of your arm, let's say for the sake of the argument, even if it were the same force over a long time produces more momentum. Same force over a more short time would produce less momentum. Now, it is bad whole lot of them since. I now know why. They are weird, scary people. I don't know the name of this, I don't know the name of this, and I certainly can't draw them. If you had a Malava Neshek in your group in Israel, if you had a security guard defending the building after we'd received an actual threat, how many people would feel that they were protected by a more powerful weapon if it were this one instead? How many people feel that this one would be the more powerful weapon? How many people didn't vote? Let's try this again. This one, the more powerful of the two. This one, the more powerful of the two. And I know nothing about guns and I can't draw. What's the visible difference between this one and this one? Quick chemistry lesson. Gunpowder is sulfur and saltpeter and several other things. Just like gasoline, you get a spark on it, it ignites in a huge cloud of hot gas. The bullet is in a chamber that is solid metal on 3 sides. This is the difference between the medieval times and the Renaissance. Medieval times, you couldn't be sure that the chamber was going to hold. You'd cock your arquebus or blunderbuss, and it was called a blunderbuss because of the number of the people who discovered that it exploded backward into their faces. Oops! By the time we invent the musket, and musketeer becomes a rank in the army, somebody who knows how to shoot the gun so it goes forward and not backward, let's assume there's the same charge of powder in here. And let's even assume for the sake of the argument it's the same mass of bullet. What is visibly going to be different in these two weapons? Kobe, what's going to be different?
The time.
Aha! We have short time, and we have a much longer time. So therefore, what must logically be true if the charges of powder and the mass were the same? Even if the force were the same, what would obviously be true is a difference between these two weapons.
Moment.
Aha, which one would have more momentum?
The long barrel.
Okay, and that is going to be expressed in terms of velocity, because the mass is going to be the same. We said in kinematics that how far you go before you deflect completely, the parabola becomes visible to everyone and you just fall down and hit the floor, is directly proportional to your initial horizontal velocity. Step 1, aim. If you're not aiming, it's not going to do much. But imagine how fast this would have to go across the room in order for the deflection, for the parabola, not even to be visible to you. That is to say that you hit the target you're aiming for. Now, in Mr. Baumstark's class, he proved that, here's the windup, here's the pitch. If you swing your bat at high school athlete speed, you can deliver an acceleration to that ball of more than 20,000 meters per second squared. The reason the ball does not leave your bat at 20,000 meters per second is because your ball is not in contact with the bat for a long time. If you're hearing the crack of a bat, if you're hearing the bang of a gun, that is something accelerating very, very, very quickly. That's what you're hearing. Questions on longer time for the force to deliver its impulse gives you more momentum? Questions on the Impulse-Momentum Theorem? All right, let's do a quick numerical example. Starting on Wednesday, you guys are going to get into lab teams. You will be issued with raw eggs that anybody sensible will leave in the box so they don't break until you're ready to use them, and 3 sheets of paper in order to make a lab egg drop case, mock-up round 1, and see if you can protect your egg within the classroom from a sizable drum. My question is, if you had your druthers, if you had all the design materials in the world, would you prefer to design a case that did bounce, or would you prefer to design a case that didn't bounce? This is, again, taking our analysis of the quantity formally building soft and putting some math on it. What's your formula for force? How are we going to evaluate this?
F equals F.
Not going to change. Keep going.
Delta.
Okay,
Yeah.
Stan?
Yeah.
F minus VI.
Fantastic.
Over
Over delta
change
T. So
which is going to have a greater delta V, VF minus VI, bounce or no bounce? Let's try it. What's your final velocity of no bounce?
Zero.
Aha. And what's the force going to be? You sure? Check your substitution.
Oh, negative.
Negative.
Okay, and if you drop this from a height of h, check your notes. What speed will it be going when it hits the ground? We've been waiting for this since August. We can finally analyze what happens when the school flips. What is the speed at which you start the impact? Check your notes. Conservation of energy or anything more recent. You drop it from a height of h. How fast will it be going as it begins its impact?
Oh,
2H
It's like
over
2H squared
That's
root.
time. That's time. There's definitely a 2 and a square root in there. Check your notes, check the formula.
Scratch.
Careful, check the formula.
GTG.
Okay. Now, what is the final velocity if you do bounce? Really, if you go this way and back the other way? It's positive. In fact, if this is down, let's say it bounces at the exact same speed, which way does it bounce?
No bounce.
Aha! What do we need here?
Positive.
No, this was positive. What's this? Negative. If you go from 2 to -2, what's your change in velocity?
Zero.
2 minus -2
4.
is 0?
Oh, 4.
It's 4. Twice as much force to stop you and turn you around as just to stop you. Conclusion, bounce or no bounce?
No bounce.
No bounce. Odd time video production.